Hi, everybody. Welcome back to Chem 121. No, we are not the only person here. Um, the other people viewing are just shy. What do we got going on today? So, there is a lab worksheet due tonight. If you can't get it done by tonight, you still have the rest of tomorrow to turn it in because the assignment will close at 11:59 p.m. on Thursday. Remember that all assignments close one day after the due date. I have been getting emails asking me like, "Hey, can I use the NQA? I can't get it in by the due date." And I'm like, "Well, if you can get it in the day after the due date, I'll still accept it." So just be mindful of that, so that you don't uh panic. I guess we'll say. We're gonna finish chapter 2 today. Density is the last section. Then we're gonna move on to chapter 3, which has actual chemistry. We'll stop doing math for a while. And then next week, I will talk about lab number 2, which is actually related to this topic that we're going to talk about here, which is density. I do need my tablet, so I have to get that out from underneath the desk. Oops. I'm going to knock over all of the Roadhog figures, all one of them, on this side of the desk. I have a lot of Roadhog stuff. I don't even play Overwatch. I just like Roadhog. Alright, so let's click over here first, and then we'll do that. Let's talk about density. You have probably heard of the term density and might have some sort of concepts or ideas about it, such as things that are really, 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 really heavy or light relative to their space. And so, for example, if I have this pile of lead shot, for instance, like the kind that is used for, like, I don't know, heavy weights, or if you are from a family who, like, reloads their own shotgun shells, like my family did. I grew up on a farm, so um, there were bags of like little lead beads all over, and they're very small bags. And so, of course, I'd be like, "Oh, I wonder how heavy this is," as a kid, and then you try and pick it up, and then it's like 75 pounds, even though it looks like it should be 10. And it's like, holy crap, that's dense, because the density of lead is extremely high. Now, other things occupy a very large amount of space, but have very little mass relative. So, for instance, the air inside this Darth Vader balloon is heated to the point where its density is so low that it causes it to float. So the balloon remains upright and doesn't fall over. And if you heat it up further, it will actually become so light relative to the density of other people. Not people. I'm seeing people appear in the chat log, and my mind is going everywhere. The air inside the balloon becomes its density is so low relative to the air outside that it begins to rise up into the air. Yeah, it's the Darth Vader balloon. I don't know where I found this picture. I don't know if I could find it again, but we're going to define density as this definition right here. So density is the amount of space, the amount of mass something has relative to the amount of space that it takes up. So there are two terms that are relevant to our equation here. One of them is mass and the other is volume. And so we can write this as a formula, which is on the next slide here. That was down there at the bottom. Now, if you mix things together, and those objects that you have mixed have different densities, and the objects themselves will not form a solution. That is, they separate into their own constituent substances, like oil plus water. Then the objects with the lighter density, or the lower density, rise to the top. And objects with the higher density sink to the bottom. This is why when you drop metal into water, the metal just sinks all the way to the bottom. But if you drop plastic into water, it tends to float on the top. There is a cat here. Hello. You may hear him crying because he is super bored, I think. He's been bugging me all morning. Is there a relationship between heat and density? Sort of, yes. I mean, so there is a relationship between temperature and density. For gases, it is the most obvious. For liquids and solids, it is not extremely relevant, except for like one exception, and that's water, that we're going to talk about a little bit more later. When you heat up water, its density goes down. We will talk about this in Unit 7 when we talk about the kinetic molecular theory. When we describe how molecules behave when you change the amount of energy they have, or in other words, when you heat them up. There's our equation right there. We can represent density in this way, mass divided by volume. Now, the units are going to depend... Oops, I thought the units would appear right there. The units are going to depend on what phase you are involving in the equation. So if you're looking at a solid, typically speaking, your mass is going to be in grams and your volume is going to be in cubic centimeters. That's very common to express solids in this density. Another one that is often used is kilograms per cubic meter. But we're not going to necessarily use this one in this class. You may see this, though, if you look it up online. For liquids, it's much more common to see grams per milliliter because it's hard to measure a liquid into a very cubic shape. Right? Liquids occupy the size of their containers. So what we do instead is we have a graduated cylinder, which could be any shape we want it to be. Generally, we pick a regular cylinder. And then we mark off gradations on the graduated cylinder such that each line represents a given volume. And so, like, we could put dashes every milliliter. And we can measure the volume of liquid easily. So, liquids are in grams per milliliter. Gases are so light that oftentimes what we end up having to do is use grams per liter. Can mass and volume be any combination of weight and volume? So, in theory, yes. However, pounds is not a mass. Remember that. Pounds has to do with your mass times gravity. Actually, we may not have covered that in 121, or that may be in Lecture 1. I honestly can't remember. So, your weight in pounds is not the same as your mass. Not just numerically, but physically. So if you go to the moon, your weight will change because gravity changes, but your mass remains the same. So we have to use mass in this case. So we can't use pounds because pounds will change relative to where you are in the universe. If you are floating around in outer space, then your weight ends up being 0, and so density wouldn't work. So we can't do that. Now, this equation right here has 3 terms, and I'm going to write them like this. If you know any 2 terms, you can solve for the third one. You just have to make sure that the units are what you expect them to be. And so when we're doing this equation, don't just throw the numbers in the equation and then magic units at the end, because you'll get the wrong answer, and you'll see how that happens in just a second here. All right, we're going to start with a really simple expression here. So osmium metal is the densest metal known. So I'm going to write the equation right here. There's our density equation. If I have a sample of osmium with mass 26.3 grams and volume 1.16 cubic centimeters, what is its density? So go ahead and calculate that using the density equation. This shouldn't be too difficult to do. So I'm going to give you like 2 minutes to do it. I'm going to pet the cat here who's still harassing me, and then we'll go over the answer. All right, we got some answers coming in. Let's go over this together. So if mass is on the top, oops, that should be an equal sign. And volume is on the bottom, then I'm just going to divide these two numbers together, and that's trivial to do. 26.3 divided by 1.16. That should be a 1 right there. My 1 kind of got screwed up. Let's see if I can fix that. There you go. And I get 22.67241379. We only get to have 3 sig figs because both these values have 3 sig figs. So the number I would report is 22.7 grams per cubic centimeter. And so that's the density of osmium. Does density mean that there's more matter? It does in the sense that per unit volume. So in 1 cubic centimeter of osmium, there are 22.7 grams. But in 1 cubic centimeter of, say, aluminum, there would only be 2.7 grams. So osmium would have 10 times more matter inside a cubic centimeter than aluminum does. Is there any case that we need to convert the mass into kilograms or pounds first? No, but I may give you the mass in kilograms or pounds, and then you'd have to convert it back to grams, for instance. In fact, we're going to see that in one of the examples coming up, where I give you volumes in liters and masses in kilograms, and they're all the wrong units. And so you have to fix that. All right, let's do another one. A helium balloon has a volume of 2.5 liters. If the density of helium is 0.1786 grams per liter, what's the mass of helium in the balloon? Now you'll notice that I'm starting these always by writing down this equation, right? So that's my advice to you. Whenever you have to use an equation, start by writing down the equation. That's not busy work. That's just, okay, now I see visually what I'm trying to do. And you can see, oh, I need this for my answer, so I'm going to solve for this thing, right? And so you should be able to do that. So I'm going to give you 2 or 3 minutes to try this problem. And we'll go over the answer in just a second. So I see a bunch of numbers, and they're similar enough, so I think people are on the right track. But the units that you're giving me are not masses. What are the units of mass? All right, let's go over the answer here. So how does this work? We're going to do some algebra. I want to solve for the mass because I know the density. That's this right here. I know the volume. That's this right here, right? So I'm going to rearrange this equation. I'm going to multiply both sides by v. And so I get d times v equals, these cancel out, m. So if I multiply density times volume, I will get mass. Yes, you do have to do algebra in this class, so it's important that you do this and don't just plug in the numbers. So now we can enter density and volume right out of the problem. We just multiply them together. That's how we're going to get mass, right? So density was this number, grams per liter. And the volume was this number. And what do you notice about volume on the top and the bottom? Well, they cancel out, right? And so when you type this in your calculator, the only unit that's going to be left over is grams. And I got 0. I only get 2 sig figs, right? Because of this. 4.5 grams. Specifically, grams of helium. So with this equation, d equals m over v, you're going to have to manipulate the terms a little bit to try and get the answer. All right. For the last problem that I have here, this is the challenging one. I have a glacier, and the glacier has this mass, 46,720 kilograms. It's not a huge glacier, it turns out, because that's not very big. 46 tons of ice is not a ton. If the density of ice is 0.9899 grams per milliliter, what is the volume of the glacier in liters? And this is the part that you have to remember. Be careful with your units. So this is the most challenging problem I can give you with density. And so I want you to try this for about 2 or 3 minutes to see if you can get the right answer in the correct units. But if you get stuck, don't worry. We're going to go over the answer in just a second. All right, one more minute. We'll go over the answer here. All right, let's go over the answer here. So we're going to need to go to this page here. I can just leave that. Okay. All right, so what's going on here? So let's write down the equation. Density equals mass over volume. What are the units of density? Well, it says grams per milliliter, right? So my answer should be in grams per milliliter once I've put something into each of these spaces, right? However, the mass of the glacier is in kilograms. That's no good, right? I can't get a density in grams per milliliter if I have my answer in kilograms, right? So I need to turn this into grams so that it matches the density. And then I need my volume to be in milliliters. So if I have a mass in grams and a volume in milliliters, and I divide one by the other, I will get a density in grams per milliliter, which is what we see there, 0.9899 grams per milliliter. Now, how do we solve for the volume here? This is problem number 2. If I have this expression, and I need to solve for the volume, you can't divide both sides by m and say, well, there we go, I did it, right? That's not how this works. This is what you would be solving for, right? This is not equal to v. This is the inverse. So this is wrong. Okay? Be careful with your algebra. I know everybody's favorite subject is algebra in this class, right? So there we go. So here's our equation. We need to get v by itself to solve for volume, right? So I'm going to multiply both sides by v. And so I'm going to get d times v equals m. Now, that didn't get my v by itself. Now I need to divide both sides by d so that these cancel. And then this is my expression. V equals m divided by d. So this is the formula that we want. Notice that this is the opposite of the formula that we had above, right? Mass divided by density will give you volume. And we just need to put in all the units like we said above. So this needs to be in grams, and this needs to be in grams per milliliter. And that will give us our milliliters. So the first thing that we need to do, now that we have our formula here, I'm trying to put that on the screen at the right elevation there. Kresnik, please, dude. No, I'm not saying come to me for attention. I'm saying go away. Stop that. You're just sitting there yowling at the at the air conditioner, which isn't even plugged in because it's January. My cat, I swear. All right. So we need to first we need to turn the mass into grams. So we have this. Here's our mass in kilograms, and we need that to be in grams, right? So we should know how to do that. Because you could set up your units like this, and then say a kilogram is 10 to the 3 grams. And that'll be your units in grams. So now that we know the mass of the glacier, we can then plug it into the equation with the density of ice, which is shown above. So the volume must be equal to mass divided by density. And now we immediately run into an issue. How the heck do these units cancel out? And this is where algebra or math 86 comes in handy again. If I have something like this, we'll do this in blue over here. If I have a fraction like this, so a divided by a over b. Kresnik, for fuck's sake, dude. Sorry, I'm cursing at my cat because he is constantly interrupting me. So if I have a divided by a over b, the fraction, what do I do to this? How do I resolve this fraction? What happens when you divide by fractions? What is that like doing? There's a special word for this, and it's not to shout expletives at your cat. So don't do that. Anybody know? Dividing by a fraction is like... Well, if nobody knows, the word I was looking for was reciprocal. Remember what a reciprocal is, where you flip over the fraction. So if I have this fraction on the bottom of my fraction, this is the same as me doing this. So dividing by a fraction is like multiplying by its reciprocal. And now these cancel out, and this is what's left. So this expression would equal b. Now, you can kind of see where I'm going with this because this is where our units are, right? The numbers, you can just divide those, no problem. 4.672 times 10 to the 7 divided by 0.9899. You can type that into the calculator. But what the heck do you do with the units? Well, units operate just like anything else does, right? So if I see grams divided by grams over milliliters, this is the only units that's left. So when I type in this expression and I get a number, this is the unit of my answer. So the volume of the glacier is going to be 4.672 times 10 to the 7 divided by 0.9899. And what I get is 4.720 times 10 to the 7 milliliters. So that's the volume of my glacier in milliliters. But that's not what the problem is asking you. The problem wants the volume in liters. So I need to take this number and do this conversion. 1 milliliter is 10 to the minus 3 liters. And that gives me the actual answer. I wrote it that way so that you could see the number. How big it is, 47,200. But I can't represent that with 4 sig figs. So this is the best and really the only way to write the answer. See, it is possible to do. We can do algebra. It's just that it's been so long, right? Like, for a lot of students, when they come into Chem 121, they're like, holy shit, I don't remember how to do any of this algebra. And it just means that you got to go back and brush up on Math 86 and 96, which is fine. Manipulate the equations and make sure that you do the proper algebra. You divide by the same thing on both sides, you multiply by the same thing on both sides, etc. And you'll be okay. This part in blue, this part everybody forgets. I teach this every quarter, and of my 50 students, maybe one person remembers the word reciprocal. And like, that's normal because you don't go to the grocery store and shop for a reciprocal. You don't get into the car and shift into reciprocal. Like, it's not a thing that comes up ever, right? Like, who gives a shit about a reciprocal? And yet here we need it. So don't feel bad if you don't remember, but do try and learn what those terms mean because we do use them in this class. So all right. I might have more of those for us to do. Maybe not of that difficulty, but you have seen that problem. There are some problems in the worksheet that are probably similar in difficulty. And you can definitely do these homework practice problems down here. So, all right. I'm going to give you a mystery medal. And my mystery medal has these properties. And I want you to tell me what it is based on these symbols. Now, in order to identify what each of those are, AG, PD, PT, and IR, you'll have to look at the periodic table for the name. So I want you to tell me the name of the metal based on these properties. So I'm going to give you a few minutes to do that. And then that's it for Chapter 2. We'll start Chapter 3. So, see you in a bit. All right, one more minute. Type in which metal you think this is in the chat once you have figured it out. All right, let's go over the solution here. So if I divide the mass by the volume, oops, I don't know why I did that. This is the units that I would get, which are the correct units of a density for a solid. And so I get this number to 4 sig figs. Now you might be looking at that and going, well, wait a second, that's not any of the answers. That's too far off. Well, when you do science, you don't always get the correct answer. You just have to pick the appropriate choice that is closest. And what that is going to tell you is that you're most confident that the likely identity would be this one, which is platinum. However, you can't be entirely certain because your answer didn't match up 100%, right? But it's definitely not silver, and it's definitely not palladium, because your answer is way too big for those. Could it be iridium? Probably not. It's more likely to be platinum than iridium, because my answer is closer to platinum. And sometimes in science, that has to be good enough. So the goal here was just to pick the one that was the closest. If it was a multiple choice test, and you had to turn it in for credit, that's what you do, right? Oh, that's the closest one to the answer I got. I'll pick that one. Turns out that's what we do in science all the time. We say, this is likely this thing. All right. That is the end of Unit 2. I don't think that there are any more examples. We already did temperature yesterday. So what we're going to do now is I'm going to go to here. We're going to take our 10-minute break because it's roughly halfway through the class. We'll get the Stardew Valley music going again. And we'll see you when we come back for the break. So, back in a bit. There we go. Had to pop in there because I had loaded a new set of slides. Welcome back. We are done with math for a little while. We may have some math like peek in here and there, but nothing like what we did in Unit 2. Unit 2 is kind of the big math chapter until we get to, oh, sorry, Chapter 2, until we get to Chapter 6. So, for Chapter 3, you're going to need a periodic table, and so here's a good one. Let me, I'll just type this into Google and then copy. And there you go. So I am posting a link to ptable, which is a periodic table that you can load in your web browser, which is super useful. I'm going to show that on the screen really quickly here. So if I could find it, there we go. So, boop. That's not super helpful as is, but there we go. So this is ptable. And it has all of the different elements that we are going to consider for various applications, and a bunch of numbers and things that you do not need to commit to memory because it's not helpful. So we're going to look at these, and we're going to explore various properties, and we're going to refer back to this at various points throughout today's lecture. So have that handy, that website, or some sort of periodic table elsewhere, so that you can refer to it when I say, hey, what's nickel? Or hey, what's copper? Or what's oxygen? Or things like that. All right. Chapter 3 involves the structure of the atom and then also things that we can do to identify parts of it. And is a very simple overview of what are the things in the atom that are reactive and interesting to us. Now, there is more detail at the end of the chapter. So you can see on my slides here, I have sections 3.6 through 3.7 are electron arrangement, and then 3.8 and 3.9 are electrons in the periodic table. We actually are not going to do those sections. So we are going to skip over these in the interest of time. Because I personally just don't care enough about electron arrangement and configurations for this level of science. There are much better things that we can spend our time doing and more practice on. So, all right. First thing we're going to talk about is what does the atomic structure look like when you zoom in really far? And so the nucleus is going to be the central part of our atom. And the nucleus is extremely dense. So dense that if I were to put a teaspoon of just nuclei, just jammed together as closely packed as they could be, it would weigh almost a billion tons. In a teaspoon. It would be the densest thing, like, conceivable. Like, neutron star levels of density. Like, stupidly ridiculous. How the heck is that possible, though? If a nucleus is that dense, how do we not all weigh billions of tons? And the answer is, well, the nucleus is very, very tiny relative to an atom. So, the electron cloud around the outside, which is this part, this region in space, where my electrons float around, is actually much farther away than is shown on this picture. This little cartoon is not a very good model of what an atom actually looks like. The actual ratio of the size of the nucleus is 1 to 52,800 or so for the electron cloud. In other words, if this red circle right here is my nucleus, and it's about 2 or 3 inches in diameter, my electron cloud would actually go 52,800 times further away. which would be on the order of miles. So a nucleus is actually very, very tiny relative to the center of the, or relative to the rest of the atom. And so you can think of an atom as being more or less like 99.9% empty space. So if I draw this as my electron cloud, the nucleus is going to be thousands of times smaller than that little tiny dot I put in the middle. So the odds of you hitting it are extremely small. And so this is why you do not weigh billions of tons, is because you are mostly an empty void. So think about that the next time you call somebody an airhead, you're really just telling them how it is, right? Or space cadet or whatever. So atoms are extremely small and tiny and are extremely empty. But the little amount of stuff that is there is extremely relevant. Now let's talk about the stuff that's in the nucleus. There are two particles in the nucleus itself, and these are called nucleons. And the nucleons that are present are the proton, which has the positive charge. That's this guy right here. And the neutron, because it's neutral, it has no charge at all. A neutron walks into a bar and says, "How much for a drink, bartender?" "For you, sir, no charge, because you're a neutron." Oh my goodness, my cat is back. He does not like my jokes, I guess. That's okay. The electrons live on the outside, and they are negatively charged. Now, what do the symbols mean? What happens when I have two charges that are the same? What do they do to each other? Think of it like if you had two magnets that had the same polarity. You put the north ends together. What happens? Is my chat broken or something? I don't know. There you go. They don't attract each other. That's if they're opposite. What do they do if they're the same? So if I had two positive charges or two negative charges, what would you like charges do? They repel. Very good. So like charges repel one another. They would push apart. But opposite charges will attract to each other. So in other words, the electrons are attracted to the nucleus, and the electrons repel from each other. And the protons repel from each other. So the protons are in the middle, all repelling from each other. How the heck do we get them to stick together? And the answer is, well, neutrons act sort of like glue. So neutrons have a very special physical property in the sense that they hold the nucleus together through what's called the weak nuclear force. And that's beyond the scope of this class. We're not going to talk about the nuclear force. I'm not sure that that's the weak nuclear force. That might be the strong nuclear force. I'm not sure which one it is. It is one of the nuclear forces. I don't know if this one's the one. That could be a typo. So, but yeah, think of neutrons as just glue. They hold the nucleus together. Now, Why don't the electrons just get sucked into the middle then? If protons and electrons attract to each other, why don't the electrons just go cascading into the center and then join the nucleus? Why are there electron clouds to begin with? And so we're going to draw a little illustration to indicate that. So here's our electron cloud in our atom on the screen here. And what I'm going to do is we're going to make another model of something where two things are interacting through a force that wants to pull them together, but yet they don't actually do that. So this is the sun, and this is the Earth. Now the Earth is attracted to the sun. In fact, it is so attracted that if it were stationary, it would get pulled into the sun and destroyed. And the sun would be like, ha ha ha, another planet in my fiery grasp. But fortunately, the Earth doesn't have to worry about that, because the Earth is trying to move in a straight line, right? So the Earth has some velocity, but it also has the effects of gravity. And I need to deal with a cat, so give me just a second. I'm going to hit mute. Alright. We had to yell at the cat again, because he's just sitting on the table yowling. For no reason. What is the effect of both of these forces? Well, one's a force, one's a momentum. But what is the effect of both of these? Well, if the gravity is always pulling the Earth towards the center, but the Earth is always trying to move away from the sun, the overall effect is that you get this. You go in a circle. And so the Earth never really will crash into the sun, because it's just in this stable orbit. It goes around and around and around and around and around. Now, in our diagram above, you can replace the nucleus, or the sun with the nucleus, and the electron with, or the Earth with the electron. We just draw that over here. So if I have a nucleus, I'm just going to draw it as a single proton. The end result is that even though these are attracted to each other, this object has such a high velocity that it wants to go in a straight line, but it doesn't do either of those things. It tries to do the average. And so electrons will buzz around a nucleus. Now, in the absence of anything else, they would just look kind of like how the Earth goes around the sun, in a very steady and regular orbit, right? But what happens when I have a second electron in here? Well, these two things push each other apart, and so this guy is going to go this way, and this guy's going to try and go this way, right? And as I get multiple electrons, what ends up happening is that anytime they see each other, they tend to do weird things, right? And so the orbit doesn't become regular anymore. It ends up being very irregular. And so what we end up calling this is we say, well, electrons don't go along orbits. Instead, we just call it an electron cloud. So that's where the term electron cloud comes from. The electrons are somewhere in the cloud. Kind of like how your information is somewhere in the cloud when you use cloud computing, right? You don't know where it is. That's where the term comes from. It's somewhere, but it's not well defined where it is. For electrons, that's how this works. The electron cloud is just a region where electrons are expected to be. They do not, however, exist on these rings that we show here. So this is just a model. And so remember that electrons do not actually revolve around the nucleus like planets revolve around the sun. Electrons can go wherever they want to, essentially randomly, because they're extremely light and they're being manipulated by very powerful forces, which are charges. Now, if you count the number of electrons and protons in an atom, you get the same number. Now, you can't tell in this diagram because there's only 4 here. The other 2 are hidden behind the thing. But in order for an atom to be stable atomic elemental matter, I use the word stable there. I don't really want to use the word stable because not all atoms are stable. So in order for an atom to be defined as an atom, we'll say that. For atoms to be defined as atoms, they must be electrically neutral. So the number of protons and the number of electrons must be equal. But the number of neutrons can be any number it wants to because there is no charge involved. And we'll talk about that later when we talk about isotopes. Now, in most cases, atoms do not care to gain or lose their electrons unless we expose them to specific conditions. For example, if we give atoms lots of light, light is a form of energy and they can absorb that. Or we could give atoms heat and they can absorb the heat as energy. Or we can expose them to other atoms that may have a reaction. In most cases, atoms just stay by themselves, but if you expose them to other stimuli or circumstances, parts of the atom will change. And the parts that change are the ones on the outside, because the outside is what you see first when you bonk it into something else. That's the electron cloud. Therefore, changing the electron cloud, or the number of electrons in the electron cloud, is the first thing that happens when atoms contact each other. And this is called, chemistry. So, chemistry is just electrons being moved around. Obviously, there's more to it than that in terms of detail, but when we look at the transformation of matter, we're just going to be looking at electrons being moved from one substance to another, and to see what happens when we do that. Now, if you do this, for example, let's suppose I removed this electron, so remove. Then what we get is called an ion. An ion has a different number of electrons than there are protons. For example, if I removed an electron, I would only have 5 electrons here, compared to 6 protons that I would normally have for a neutral atom. Now, if I remove electrons, this does affect the charge. For instance, if I have 6 positives and 6 negatives, they would cancel each other out and I'd have no charge. But if I were to remove an electron, I would have a leftover positive charge that is not countered by electrons. And this has consequences that we'll talk about later. We'll talk about ions more in a little bit. All right. The first few problems in the textbook have to deal with just terminology and lingo, point at the proton in the picture, that sort of thing. All right. So let's detail atoms in a little bit more concrete way. So, like, let's ascribe numbers and stuff to them. So we're going to do some counting. And that's going to help us ascribe properties to our atoms that we can then use later on when we study other sorts of situations that we can put atoms into. All right. How do you define an atom in terms of something it has that we can give it an identity? And the answer is we define it by its atomic number. The atomic number on a periodic table is oftentimes a big integer written either in a corner or centered at the top of the element box. It's always somewhere in the top part. Now, some tables put it on the top left, some put it on the top right. For example, P table here, if I open P table again, it went to sleep, but P table puts them in the top left. So, yeah, we still have P table selected. So there we go. So here's P table. You can see that in the element I have selected, hydrogen here. Its atomic number is 1. It's the number in the top left here. There it is. Oh, my cursor is invisible. There it is. Now, if I pick something else, so here's rhodium. Rhodium's atomic number is 45. Arsenic's is 33. Potassium is 19, and so on and so forth. Everything has an atomic number. What does that mean? The atomic number is the number of protons that atom has. So everything is defined around the number of protons. If you have 1 proton, you are hydrogen. If you have 2, you are helium. If you have 3, lucky you, you're lithium, and so on. We don't use the number of electrons to define stuff because the number of electrons changes. But changing the number of protons is extremely difficult and does not happen in chemistry. So that's convenient for us. We can use the number of protons as a name. And so there's more examples on the screen there. Sulfur has 16 protons, carbon has 6 protons, oxygen has 8 protons, neon has 10, and so on and so forth. We're going to use this variable here, Z, or Z if you're Canadian like me. Z is going to be the number of protons. We're just going to replace Z in a symbol later with the number of protons. So whenever you see Z, that's the atomic number. Now we're going to introduce another variable, A. A is what's known as the mass number. And the mass number is protons plus neutrons, because they make up the majority of the mass in the atom, and they make up all of the mass in the nucleus. So that's where that term comes from, mass number. It's the mass of the vast majority of the atom. Electrons essentially weigh almost nothing. All right. Now again, remember that if atoms are neutral, the number of protons and electrons must be identical, and therefore Z would tell you the number of electrons for a neutral atom. So neutral carbon has 6 protons and 6 electrons, and you know this because its atomic number is 6. Boron has 5 protons and electrons if it's neutral because its atomic number is 5, and so on. Now, what about the mass number? Can you figure out the mass number from anything on the periodic table? The answer is no. The mass number is an integer. It is a count of the number of protons and neutrons in an atom. But the number that is shown on the periodic table on the bottom, the mass number, does not do that. It does something different, and we'll talk about that in Unit 6. So for now, if I go back to P table here, this number on the top is going to be very helpful to us, this right here. But this number on the bottom, we're going to ignore these. Ignore the the atomic masses on the bottom. They are not mass numbers. Okay? Be careful. All right. Let's do an exercise to describe elements in more detail using a symbol. And we're going to use these symbols with numbers to identify specifically what atoms we are looking at so that we can convey that information to other people. For example, your boss, or your lab partner, or me. So here's what we do. I have written on the screen curly brackets E. What we're going to do is we're going to replace curly brackets E with the symbol of the element that we're interested in. So we're not going to have brackets. We're not going to have an E. We're not going to have anything. That whole symbol right there will just be turned into whatever elemental symbol on the periodic table. Again, here's all of them that we're looking at. So for instance, if I wanted to look at potassium, I would do this. I would get rid of everything, and I'd write K. All right, that was step one. Step two, as a subscript in front of the symbol, we're going to write the atomic number. That's Z. Next, as a superscript in front of the elemental symbol, we're going to write the mass number. And then finally, the last step in this process is celebrate because it's done. So this is known as complete chemical symbol notation. It's also known as isotopic symbol notation. Or if you're like me, I just write ZAE notation. I've sort of made up that term. Hopefully it will catch on. It's way easier to type than that whole sentence. So that's where I go with that. So let's do an example. Let's suppose that you want to reproduce a symbol for a carbon atom with 6 protons and 6 neutrons. What would you write as the bottom number, and what would you write as the top number? Type your answer in the chat, and then we'll fill it in and see how you did. All right, so we have some numbers in there. We want to put a number on the bottom for Z, for carbon. And we want to put a number on top for A, for carbon. So if I have 6 protons and 6 neutrons, its atomic number would be 6. So we put that at the bottom. Now, if it had 6 protons and 6 neutrons, the total number would be 12. We'd put that up at the top. And so this would be the symbol for an atom with 6 protons and 6 neutrons. All right, let's do another one. Oh, let's do another one. I'm going to just clear the screen real quick here. Let's do one for this. An atom with 28 protons and 32 neutrons. So what I want you to do is first identify which element I'm looking at. And then tell me what goes in the space for Z. And what goes in the space for A. So type that in the chat too. All right, hopefully you've had a second to write something down and think about that. So first what we need to do is we need to look up which atom is 28 protons on the periodic table. So if we go over here, oops, that's the wrong window. That is the YouTube stats. There we go. And we find element 28, we would find nickel. So I'm going to write that down, nickel. My pen didn't work. There we go. So I have nickel. Then I have to write... Well, first I have to get rid of this so I can show you that I've written that. Then I have to write Z. Z is the atomic number. That's 28 protons, so I have to write this. And then for A, that would be 28 protons and 32 neutrons. Well, 28 plus 32 is 60. So I would do this. So this would be the symbol that you'd write down for an atom with 28 protons and 32 neutrons. Very good. All right. So now what I want you to do is I want you to do that process for all of these atoms shown on the screen. Down at the bottom, I'm just asking you generic questions about how many of this thing does each of these indicated atoms have. So looking at the notation, tell me how much each of those has. Assume that all the atoms are neutral. Okay? All right. So write the ZAE symbols. Type in the information as best as you can in the chat. Like writing, say, I don't know. So for the last example, you could do something like this. Z equals 28, A equals 60, nickel. So like something like that in the chat. So I know that you are almost finished. Okay, I'm gonna give you about 4 minutes to do these questions. We'll go over the answers together in just a bit. See you soon. All right, one more minute. We'll go over the answers here. All right, let's go over the answers here. Sorry about that. I got distracted by an email. So let's do this. Ah, that's not what I wanted. That's also not what I wanted. That's what I wanted. All right, so write the symbol for the following atom. So I want an atom of chlorine. So first we got to write its symbol. Well, according to P table, the symbol for chlorine is Cl. Keep in mind that on chlorine here, this is a lowercase L and not an I. Okay, so there's no Ci on the periodic table. That is C lowercase l. Oh, that's okay. That can all just go away. All right. And I have 16 neutrons. Well, first of all, I got to look up how many protons chlorine has. And according to P table, which I have to capture again here. I have no idea how this will show up because it's a different window. There we go. So if I go over to chlorine, boop, and I click on it, I can see that it has 17 protons. So that's what I'm going to do, is I'm going to write down 17 for its atomic number. So there we go. And then chlorine has 16 neutrons in it in this example. When I add those together, I get 33. So this would be the symbol for an atom of chlorine with 16 neutrons. Would look like this. All right, an atom with Z equals 25 and A equals 55. Well, if Z is 25, I just write that down. And if A is 55, I just write that down too. I don't need to worry about anything other than that, yeah? Then I have to write down the symbol, and I have to figure out which element is number 25. So if we go back to the periodic table, which one is it? Where's 25? Hey, there it is. Boop. Mn, or manganese. So that would be the answer to number 2. The third one's a little bit of a math problem. What number plus itself equals 36 if I have the same number of protons and neutrons? Well, you could write this like this. And solve for x. Ah, there's algebra in everything, isn't there? It's all over the place. So if I had 18 protons and 18 neutrons, my mass number would be 36. So that must be this atom. And then if we go back to the periodic table and find element 18, there it is. It's argon. I tell you a good joke about argon, but all the good jokes about it are gone. Womp, 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 womp. All right, so there's those answers right there. Actually, now that I think about it, we don't have to actually do this one on that page. We can do this here. So how many protons does this atom of silicon have? Well, remember, Z is the atomic number, so there must be 14 protons in order for it to be silicon. How many neutrons does this atom of potassium have? 1939. Well, remember that the mass number is protons plus neutrons, right? So if protons plus neutrons equals 39, but the protons are 19, how would I figure out just neutrons? Well, you can subtract them, right? Because then this will just get subtracted out. So the number of neutrons will always just be the difference between Z and A. And then finally, how many electrons does sodium have in this atom? Well, if it has 11 protons, it must also have 11 electrons because it is atomic neutral sodium. All right, that's all we're going to be able to have time for today because there's only about 5 more minutes of class. And everybody seems to be very tired and sluggish, so we're going to call it a day early so that you can take a nap or something. I don't know. But if you have any questions, let me know, either over email or in the Discord. Lots of people are using the Discord to ask questions. That is excellent. Quiz number 2 is going to go up later today, once I have some time to do it. Actually, I might have time to do it after class. That will be due 1 week from today, which will be Wednesday the 26th, it looks like. So make sure you do that by next week. Quiz number 3 will be going up next week when we come back for class on Monday, because we're going to finish Chapter 3 then. Then we'll continue working on Chapter 4, and we're pretty much back on track at that point. So our goal is to get through the first 5 chapters before exam number 1, which is at the end of week 5, and we're doing all right. So I do want to thank everybody for coming out to the lecture. If you have any questions, again, email me, message me on Discord. Either of those works. Lab number 1 is due tonight. The closing time for that is tomorrow evening, so you have 24 hours after tonight if you can't get it in. Again, make sure to ask questions if you have any concerns. And yeah, otherwise, have a wonderful weekend. Thanks for watching and take care. See you next week.